Please come down.
Yes.
Listen, Yuli Nazarov.
Thank you. So I go on with my lectures, and I want to switch to something more interesting. So, of course, it's nice to know that normal electrons can be described by scattering matrix, and this approach is overwhelming. You can get all details of what happens with electrons upon the transport. Full counted statistics is an example for it, but it is a rather boring system. Normal electrons, and I kind of implicitly assume that the scattering doesn't depend on spin. It turns out that the same apparatus, scattering matrix, can be almost universally applied to much more interesting systems. Interesting from many reasons, ranging from practical applications to Majorana modes, whatever. I will exemplify the statement, and I will talk about Andreev scattering in superconductors and about spin scattering. I love Andreev scattering better, so I don't know how much would I say about spin scattering. In principle, it's 50-50, but we will see how does it go. Right, so let's see if it makes sense to look at outline. Yeah, I will talk quite a while about basics of superconductors. For those who know more about superconductors, it will be fun how little you should know about superconductors to understand everything. For those who don't know, they just get minimal knowledge. Right. And again, here there will be the same story, which I illustrated for normal transport, as you remember. The conductance, the normal electrons, does not depend whether you make your nanostructure from metal, from gold, from semiconductor, from wood. The same approach, the same formula will hold. Everything is expressed in terms of scattering matrix. If you go to superconductivity, materials seem to become very important. There are only few superconductors which can be used in technology, and they're very big technological revolutions. If people really get underneath yet another superconductive material. But from theoretical point of view, from the point of view of practical understanding, this doesn't matter. It only matters there is a superconductor, and that's it. You could use the same scattering model for nanostructures which has been used for normal electrons. I guess it was first recognized by people slightly later than Josephson theory, perhaps in the beginning of the 60s. And yeah, actually, methodologically, it was a great discovery. Right. I don't know, I don't want to go through all these points, just mention the Andreev scattering and spin scattering. Fine. A little bit childish slide, but anyway, I feel obliged to tell about this. Superconductivity has been discovered by government owners, and that was a discovery which really could not be predicted theoretically. It could not be predicted theoretically in the beginning of 20th century when it has been discovered. Suppose by chance superconductivity has not been discovered till this year, I don't think we would have theoretical predictions. So it just came on the way. And so do I have time for a joke? Here we go. Government owners was a very practical man. He was inventor of new methods of making helium liquid and achieving low temperatures. So he had a lab in Leiden, and there he had a system of pumps for about a week. And in a week he got several gallons of liquid helium, and he could make experiments. So, and he wanted really to do all experiments possible. So he did experiments by himself, all assistants, all students have been doing experiments, but he was short of hands. So what he did, he got the streets of Leiden where there were some teenagers, hanging, had nothing to do, and for small pennies, he invited these teenagers to the lab. He was so desperate. After that, there was a certain educational technical school in Leiden, which has grown from his attempts to involve street hooligans to practical. Right. So one of these heading hooligans was attached to supervise experiment on measuring the resistance of mercury, and it appeared to be that he has broken an expensive device or meter at some stage. One could see it really from the plot. The device showed zero resistance, so that boy was sent out immediately without paying. That's why we never know the real discoverer of superconductivity. All right? But anyway, Professor Kamenonis was diligent enough to repeat the experiment and to see that all meter always broken at the same temperature, depending on the material. That's how superconductivity came about. All right, zero resistance, a Meissner effect, which amounts to the statement that magnetic field is expelled from superconductors. You want to put the superconductor magnetic field. There was a force acting upon it. So there was we in Delft seduce schoolboys by making levitation experiments. There was a magnet and a piece of old superconductor upon, and it levitates. People are watching and get seduced to go for applied physics. Perhaps you have seen it once also here. If not, I would recommend it. It's a really fascinating experiment. Meissner effect. Magnetic field is expelled, which means that there are currents, surface currents, appearing if you want to push a conductor to magnetic field. And that is strange because these currents go by themselves without any dissipation. This is the currents, supercurrents, as they call them. Right. And it took I guess, more than 50 years. It was just not ordinary 50 years we have now. It was a 50 years of revolutionary explosive development of physics, where most of modern physics has been created. It took 50 years to get to theoretical explanation of it. Right, so let me quickly summarize what was the discovery to stress the level of my outlining. When kids got first questions about how children came about, some parents talk about storks bringing children. So that will be the same level of explanation. Cooper pairs are formed at some stage. At this low temperature, Cooper pairs are formed, electrons come together and they form particles of charge 2e. Right. These particles are bosons. So being bosons, they form a condensate. So all these particles just came to a single quantum state. That's why superconductors are kind of macroscopically quantum. They're macroscopically quantum, and it is extremely important that the superconductivity, that the condensate of this kind has a phase. The corresponding order parameter is complex. With some, we can explain superconducting currents in this way. How come? The energy doesn't depend on phase if you change the phase very slowly in space. It means if you have a gradient, with gradient, the energy cost will be also very small. That's why you can arrange superconducting currents with very low energy cost. But if they're proportional to gradients of phase. Another question, why gradients of phase would lead to currents? And that has everything to do with the fact that very strange symmetry has been broken in the course of superconducting phase transition. It's not like the rotational symmetry like in magnets. It's not translational symmetry as it happens in many structural transitions in crystals. It is a symmetry which normal people would not broke at all because it's one of the most fundamental symmetries. It's gauge symmetry. So superconductors provide spontaneous breaking of gauge symmetry. And it amounts to the fact that the charge is not conserved in superconductors. If you don't believe me, stay with me. We will look in details how and why it is not conserved. All right, that was short introduction to superconductivity. Okay, perhaps for many of you it was the last short introduction to superconductivity. Perhaps somebody has heard about it first time, but I don't get it. Good. Let me go a little bit more microscopically. I would need it. I want to talk about the spectrum of charged excitations in superconductors. And let me first start with normal matter without superconductivity. What kind of excitations do I have? Here, horizontal axis, I plot kinetic energy on the particles, and this is Fermi energy. So all states below are filled with electrons, and all states above are empty. Then what can I do? I could put an electron to empty states. I can extract an electron from occupied states. So I have two sorts of excitations in superconductor, in normal metal, electrons and holes, and those are gapless. The energies of these excitations are very small at Fermi surface, and all theory of metals is based on this. Fine, that's why metals, look at that. It costs very little energy, infinitesimally small energy to create an electron-hole pair. Fine. Let's see what happens with superconductors. And again, my intention is to give really minimalistic introduction. I already talked at the level of strokes. Right? Let me imagine a hole in superconductor. It can interact with condensate, and it can add a Cooper pair into condensate, thereby it will be converted into electron. The same will happen with electron. It could dump electron pair, add Cooper pair to condensate, and become a hole. These processes are coherent. They can, they rather mix their functions of these objects than cause real transitions. So by electron and hole states in superconductors are mixed. This is manifestation of what I said. Superconductors break gauge symmetry, break the laws of charge conservation. Right. What's the result of this mixing? It's level repulsion between electrons and holes. So the actual charge excitations in superconductors are mixtures of electrons and holes, are superconducting gaussian particles which doesn't have definite charge. And what is important, that the spectrum is gapped. There is a minimal energy to create a charged excitations. If you're not confused at this point, you have to be at least kind of open, because what is the spectrum which I have shown, is typical for semiconductors, which appear to be insulators at low temperatures. But I'm talking about superconductor. So how can react on this? I understand that's rather silly remark, but still, who can respond? Why there's a current? Why they conduct?
Because here consider only electrons, but really conductance is for purpose. This is excitation under the ground state of purpose.
Yeah.
Not that something that really conduct.
Yeah, common intuition tells us that the current is due to charged excitations, but not in superconductors. Superconductors, the current is a property of condensate. where phase gradients can be formed and thereby current is flowing. Good. That's it. I guess I completed a series of superconductors. Let me turn to charge transfer. Let me immediately concentrate on the most remarkable effect which comes here, and to this end I arranged the following nanostructure with a metal on the left, with a superconductor on the right, and as to nanostructure which connects to it, it is convenient for me to make it ideal, like we have seen in quantum point contacts, no reflection. So normal electrons would just go through in proper channel without noticing that they get through. Here, if one likes paradoxes, one finds one. Why is it true? Because let us consider an electron which goes to the right, and it cannot be reflected. There's nothing who could change its direction. But if energy of the electron is smaller than this gap, there's no place for it to be in superconductor. So it could be neither reflected nor transmitted. Something else should happen. What has happened has been understood by Andreev. I guess it was early 70s, if I'm not mistaken.
64.
64, yeah, yes. Yeah. I was already born by this time, but I could not really follow literature. Right. Let us understand what has happened. An electron, which we have sent through this ideal nanostructure, goes to superconductor and increases the number of Cooper pairs in this superconductor. And it gets back as a whole. That's fine because we have seen that in normal metal, electrons and holes could have the same energy. Right? So let's run some foolproof check. Let's check if this energy, this process satisfies concentration laws. Energy is conserved. Charge is conserved in this funny manner. Each electron, which we have said changes something in its conductor, it increases its charge. But since the condensate is kind of infinite, it doesn't see this current change unless we make superconductor finite. Right. The momentum is conserved, almost conserved to be precise. Why is it so? Because electrons and holes with the same momentum, they have opposite velocities. The hole can be seen as kind of electron moving back in time. So that's why the process can occur without any sharp potential which would change its momentum. It doesn't have to be changed. All right. Spin is conserved. That's easy to imagine. I think I've forgotten to say that Cooper pairs are singlets. They consist of electrons with opposite spins. That's why everything is fine with spin concentration. Right, that was Andreev reflection. Let's see if there's an attempt to smuggle some formulas into transparency, so how to understand it not on the language of particles, but on the language of waves. It will only work if the waves, either in superconductor or in its vicinity, have two components. Let's talk about electron and hole component. Right. So I need a Hamiltonian which would work with these two component wave functions. This Hamiltonian is made by blocks, and what we have here are just usual Hamiltonians, and they act on electrons and holes without mixing them. What mixes electrons and holes is superconducting order parameter. Right. And if you want to describe stationary states, you come with this Pogolubov-Dejan equation, which is analogous of Schrödinger equation for superconducting world. Right. Let me talk about magic mirrors. We've been talking about one-dimensional geometry. If one considers higher geometries, it turns out that electron which comes to superconductor, that one, is reflected as a hole, and the hole goes precisely in the same direction. Oh, that already looks like magic. It is not, because if you have seen a bike today and look at his back, then yeah, you see that it can be realized without any quantum mechanics or any magics. What is important for this reflection is that the phase which is accumulated for electron can be compensated by a phase which is the hole inside. So if one considers the phase along this path, the phase difference is zero. Right. Let us. I have already tried to picture it. Let us think that this wave process occurs in some scattering media. So each cross would scatter this electron randomly. And without this property, without this magic of this mirror, you could never collect back the scattered wave. Like if you try to look through the fog, you would not, you don't see anything. But this process actually cancels all the phases, and this trajectory goes back, repeating all scatterings. So if you have a fog and magic mirror beside, you would see everything clearly. You could see your own reflection in this mirror very clearly despite the fog. Right. So I was talking about the Pogolubov-Dejan equation, and about its properties, about magic mirror one can arrange with the help of Andreev reflection. All right, let me. Maybe I would expect some questions, but anyway, let me go. Let me give more details about important property, which is again missed in a very simple picture of a reflection. If we talk about the reflection of particles, we miss something important, and this is the phase difference between incoming and outgoing wave. Right. In order to get this phase difference, I need to understand what is happening in superconductor, where, for instance, where incoming electron wave enters this superconductor, what will happen to this wave? Since there is no space for this wave, there is no space, there are no states for this electron and this energy, it should somehow be damped exponentially. Right? So it's exponentially damped, and this happens at
Yuli.
yeah. Oh, sorry.
Could you repeat why do we do not have a phase difference?
If we talk about scattering of particles, that's what I said, you send an electron, you get a hole, the phase never comes in my discussion.
I meant the magic mirror.
But if I talk about waves, the phase is important. I mentioned in my story about magic mirror that the phases are important. And now I want to continue. But when you talk about scattering as about what happens to particles, you don't need, you miss that phase issue. More questions? Right, good. So there's exponential decay, and some phase is accumulated at certain lengths in superconductor. It might be confusing, and I kind of know very much adult and advanced scientists for whom it's been a discovery that this process of accumulation of electrons and holes happens at pretty long scale. It doesn't happen at atomic lengths, it happens at the accumulation lengths in superconductor, and for pure superconductors, for instance, this is inversely proportional to delta, and delta is a small scale. So I've heard of superconductors with coherence length about 100 microns. That was very effective, exceptional, but one could easily think of 100 nanometers, which is pretty big in atomic scale. This 100 nanometers can be eventually much larger than the size of nanostructure. Nevertheless, it is not important for us. Yeah. What is important for us, as for professional scatterers, is only the result of this process, only the phase which has been accumulated in the course of this condition. This phase becomes superconducting phase, the phase characterizing superconducting parameter, this is natural, and it also becomes energy dependent term, which will become important for me when I will talk about Andreev bound states. But at the moment, it's enough to understand that we have superconducting phase and some energy-dependent contribution. This contribution changes at the scale of delta of the gap. Fine. So now I know what happens in the course of a wave reflection from the wave, from the point of view of the wave. I know the phase. Let us see. Let's go to more interesting things, and to start with, we make this nanostructure non-ideal. What we can say now about transport processes, in that case, an electron, there's an electron, incident electron which I sent, can be reflected in two ways. There's an amplitude of Andreev reflection and an amplitude of normal reflection. Because nanostructure is not ideal, it can also reflect electrons in a normal way. So I want you to help me to understand what is the current in two situations. Just a general situation, and second for the situation at low energy. To start with, let me recall current channel. Let me recall what we know about normal electrons. So there will be incident electron, and part of it will be reflected. So the current here will be proportional to incident electron minus reflection coefficient. And reflection coefficient is the modulus on the amplitude. So please help me and give me the answer for the case when both Andreev and normal reflections are present. How can I generalize this formula? Yes?
So now the reason of the current in this system is the difference of phase. To establish current, we need to current rise to establish phases equal. So main effort to give us a current is unfair reflection. That's how I understand.
It was an hypothesis, but okay, this is not a problem. One doesn't have to think of the base, one doesn't have to think about chances to be Andreev reflected and normal reflected. Given these chances, what is the current in the channel? Or, in other words, what part of incident electron is really transmitted? If there is normal reflection, it's obvious it's 1 minus Rn. I wanted to include the coefficient of Andreev reflection to this formula. Yes? Yes, you're right. Because it's the whole going in opposite direction, the contribution to the current should have opposite sign. Here we are. 1 plus Rn minus Rn plus of A. Right. If you go back to previous situation, if normal reflection is 0, we would get 2 electrons for each electron sent. But I promise not to joke about this today. You can make your own joke about this application. Fine. Now, even I have a question that we need to break. But anyway, now first, yet another question. What happens at a low energy? How one can transform this formula, simplify this formula at low energy? When electrons cannot get into superelectron. Yes?
In general, the reflection is suppressed. So it's only RA equal 1. And this
Let's see. What I can say is that in this case there is no probability of transmission. So the electron must be reflected either in normal way or in Andreev way. So the sum of, let me write it as equation, the sum of Rn plus Ra should be 1. This is the way to simplify this problem. Fine. Now I want to do what I promised. I want to apply scattering theory to know for this situation. So let's see what I get. I have a scatterer, and I take it pretty normal. So all scattering processes are what we have started. But it is close to superconductor. So electrons traversing this scatterer can also be reflected in Andreev way. Okay? As in this double barrier problem, that can happen in many ways. This is the simplest process of Andreev reflection. This is more complex process when electron is reflected once, then it is reflected from the back side of the nanostructure, get back to superconductor, yet another Andreev reflection. So there are all these possibilities. Let us see, we can do it with our hands, very simple. Let us simplify once again. Let me consider one single channel where this happens. So scattering matrix for electrons is like this. Now I recall that holes go in opposite direction, and it means that wave functions have to be complex conjugated. So this is the reflection matrix for the holes. All right. That's actually why phase shifts of electron and hole cancel. And besides, I should remember that there is some Andreev phase coming into play. So now I do the same bookkeeping of trajectories we did for double barrier. Just specify this term as the simplest process. Let's see what happens for, so I'm specifically looking at the amplitude of Andreev reflection. I could think of amplitude of normal reflection as well. I concentrate now on amplitude of Andreev reflection. Okay, what happens? First contribution to this amplitude. Transmission as an electron. Phase shift due to Andreev reflection and this interface. And then transmissions through the same scatter as a whole. So transmission amplitude comes at least twice. Right. Let me understand what I will get if I repeat this process. Okay. This is transmission, Andreev reflection, reflection from the backside as a whole, Andreev reflection, reflection from the backside as an electron, yet another Andreev reflection. And only after that it transmits back as a whole. Good. Now I can sum up everything together. And the question is ready. It's again geometric series. It is easy to sum up the contributions of infinitely many amplitudes with an arbitrary number of bounces between the backside of the scatter and the superconductor. That's what is the answer. Right, what is to notice, I'm still talking about amplitude, but here there are no amplitudes, there are transmission and reflection coefficients in this channel. How come? I always have amplitudes in this combination. So the lowest order amplitude is proportional to transmission coefficient to the square of transmission amplitudes. Good. If one really wants simple formula to exercise fifth grade algebraic skills, we can simplify it and consider the regime of very low energies, very small voltages applied to superconductor voltages which are smaller than superconducting gap. All right, in that case, you can put the phase to minus pi over 2. So all these factors become I, square it, that's the Andreev reflection test, Andreev reflection probability, in terms of scattering process, of scattering properties of the nanostructure. We didn't take anything from superconductor, but Andreev reflection phase. Good. To check if T is 1, it is 1. Andreev reflection first, everything is Andreev reflection. If T is low, Andreev reflection chance is small. Right. So just if one believes the scattering approach, this complex calculation becomes child's play. You just need to remember geometric series. You don't have to know whatever its functions, diagrams. Fine. Let me look at the examples for particular realizations of vectors. First of all, I want to generalize it. So the conductance is contributed by all channels in the structure. So it is a sum of these channels with this function. These two come from the fact that two charges are transferred, not to forget about this. Then different types of conductors are manifested here very prominently. Again, if you take normal conductor, we measure conductors, we could only know the total sum of transmission coefficients. We don't know whether they are small or big, or some small, some big. We can easily see it by connecting one end to superconductor. In this case, if you talk about tunnel junctions, we have sum over t squared. T squared is smaller than t. Transmission coefficients are very small. That's why it's much, much smaller than normal conductance of tunnel junction. That's eventually what we see in Josephson types. Right. If you concentrate on ideal propagation, we have a factor of 2. I was not joking about. We have a factor of 2. We send 1 electron, we get 2 electrons transferred. For any other sort of transmission, for any other class of conductors, one needs to know the transmission distribution to get the answer for Andreev conductance. And the most typical case is diffusive conductor. But that appears to be very confusing case for completely diffusive conductor. The Andreev conductance and normal conductance are just the same. Why is it so? Because diffusive conductor has simultaneously transmissions of low, transmission eigenvalues of low transparency and transmission eigenvalues of high transparency, and they compensate each other in phase conductance. Fine, that was about conductance, and I think I need to accelerate. Anyway, I love it better than spin. So let me go to Josephson effect. Let me describe it in my language. You have heard already about Josephson effect for a while. Let me first define the situation. So now we have 2 superconducting leads and some connection between the 2, which is going to be nanostructure in several minutes. But let me first outline what Josephson told us about this in the age which was younger than the age of Moscow. Not to discourage you, but just to characterize Josephson. Right. So first he told us that in this contact there will be a supercurrent. Okay, if you believe that supercurrents are due to gradients of superconducting phase, that should not surprise us. So instead of a gradient, we have a drop of the phase at a junction, so there might be some supercurrent, which depends on phi. It is essential that it is periodic in phi. Why? Because other parameter is periodic function of phi. Right. Then, this is what is called Josephson relation. And I guess Josephson was really the first. I mean, sometimes young age lack of knowledge really helps you to formulate non-trivial things. He has figured out how this breaking of gauge invariance eventually leads to this formula. The change of phase in time amounts to the voltage at this contact. One can see it in different ways. Let's move phase, you get voltage. Let's apply voltage, you get the phase running in linear fashion. That is AC current. So if we manage to apply voltage to Josephson junction, the current will oscillate with Josephson frequency. You heard about Shapiro steps yesterday. Shapiro steps are just kind of heterodyne detection of this phenomenon. Okay? Right, we still at the level above. Coulomb transferred. I find it important to share about or just remind about the thing which might be triviality, but yeah, it is the fact that this current, supercurrent, which exists also in ground state, the state of some thermodynamic equilibrium, can be expressed in terms of the energy of the junction, namely in terms of its phase dependence. Let us see. When I'm talking about such relations, very general relations, it's always useful to talk to experimentalists because they kind of have a better feeling for this. And this derivation eventually has been taken from Mike Tinham, and it goes like follows. Current and voltage. The energy change of the junction by virtue of energy conservation should be just power, current times voltage. Right. From the other hand, voltage comes from Josephson relation. So now we know what is the derivative of energy with respect to time. And from the other hand, it must be derivative of energy with respect to phase times time derivative of the phase. You compare these formulas, you got what I put here. Current is a part of the coefficient, the derivative of energy with respect to phase. Some point which is usually missed. I'm talking here about whole energy, not really concentrated on the junction, but the energy of the leads, of all possible excitations in the leads. These leads go from the fridge. There are also some energy associated with this. The whole energy, the energy of the whole universe, if you wish. But the current is given by its phase-dependent part. It is contributed, therefore, by particles who fill both superconductors. So that's why this energy and current can be attributed to nanostructure, can be attributed to the contact between two plates. Right. Let's see what we can do with Josephson contact and nanostructures. So I take two superconducting leads at different phases. I put a scatter in the middle, and I want to understand what is going on, what are the wave amplitudes I have to look upon. All right, in this case there are electrons and holes coming to nanostructure from the left, coming from the right, and also outgoing ones to the left and to the right. Okay? So there are like plenty for amplitudes on each side of the junction. First of all, they are related by scattering matrix of the nanostructure that expresses outgoing waves in terms of incoming waves, and it does so separately for electrons and holes, right? That's why it has such a block structure. Electrons and holes. Fine. Let's see what Andreev reflection gives for us. It just gives the opposite. It mixes electrons and holes. Thereby, if you know incoming wave, you can get it as outgoing wave. Let's understand what happens, what we can write now. Outgoing wave is incoming wave times scatter matrix of the nanostructure. But if we use scatter matrix of Andreev reflection, we get back to another wave. This is not scattering setup we have studied so far. Why is it so? Because there are no waves coming from infinity and getting back to infinity. So it looks it doesn't work, the scattering approach for this situation. But let us look at it a little bit more mathematically. Let's understand that this equation for magnitudes will have a solution if the product of these two matrices has eigenvalue equal 1. All right? Next step is to understand that these matrices do depend on energy, and energy-dependent part of Andreev phase is responsible for this expression. Let me flip it a bit back. Let me remind this formula. Andreev reflection phase does depend on energy. So, right point to take that tuning this energy, we can always achieve eigenvalue 1, and precisely this energy will have bound state. Bound state concentrated at the nanostructure. Right, sir. There is a famous expression. I think Carl Benacker was responsible for this, which gives your energy in terms of transmission coefficient of the nanostructure and the phase applied to the fine. If you plot this energy versus phase for different transmissions, we see that for all transmissions and zero phase, and also minus pi over 2 plus over 2 is periodic, that for zero phase, all energy levels are very close to spectacular gap H, gap H, sorry. Then depending on the transmission, they either deviate very little at small transmissions or go deeper, and at ideal transmissions they just hit zero at point 05. Yes?
Could you repeat why the first equation holds?
That first equation. Right. So now I understand how waves are related to each other by two scattering processes. Normal scattering, that was the previous page, and Andreev reflection. Normally I would just express outgoing waves in terms of incoming waves. I cannot do it now because there are no waves incoming or outgoing to infinities. That's why I can express, for instance, outgoing wave in terms of outgoing wave itself. Nothing comes from infinities, so I just work with the waves which are inside the junction. It might be the end of the action, the end of the calculation. For arbitrary scattering matrices, I just have no solution to this question. No wave can live inside the junction.
But what are exactly the side of and side of?
Those are scattering matrices for Andreev reflection and for normal reflection.
But the states that are considered, the incoming and outgoing, where do I have to locate them in the junction?
Like it is from here. So there are two spacers between superconductor and the nanostructure. You can go to the spacers and look at the waves that go to the left or to the right. They have some independent amplitude. There can be also electron waves and Hall waves. So for each spacer, I have 4 independent amplitudes. Now I just look how they are related. There are waves which go to the junction and are reflected. So that works as usual, but there's also a process which brings these waves back. Right. That's why I can express initial wave in terms of the same wave. Usually, again, this equation doesn't have any solutions, but there's a particular case of the matrices when this product has eigenvalue 1. And if we change energy, we can tune these scattering matrices to this property, having eigenvalue 1. And precisely this energy we will have Andreev bounds. With energy given by this formula. So again, it was fun, it was a revelation to understand that the energy of the state doesn't depend on properties of superconductors except the energy gap. And it's completely defined by what is happening in the contact. To add more facets to the fun, in kind of natural scale, that can be junction, one can think of break junctions, and the junction can have 1 nanometer size, just a couple of atoms. Andreev reflection, as we learn, will happen at the scale of hundreds or perhaps thousands of nanometers. So bound state will eventually mostly live in superconducting leads under the barrier. The wave functions will drop exponentially in this area. Still, it will live at quite big scale. Andreev states in metals, they persist at very big scale, much bigger than extension. Still, this is bound to the junction. Why? That one can make such a state to be bound at such a big scale with very small junction. Okay, let me go through. Josephson energy. We are talking about excited state. Josephson energy, the energy of Andreev bound state is positive, but it is also reflected in the energy of the ground state. One can see it as a certain symmetry of Bogoliubov-Dezhenko-Hamiltonian. So, in fact, the ground state depends on all these excited energy states in every channel. So, phase-dependent part of the ground state energy is just a sum of Andreev excitation energies with opposite sign. To make it more confusing and perhaps to give some mnemonic trick for this. This formula looks natural, but it is actually derived for spin degenerate case. So here, there is summation of it on the over orbital degrees of freedom. One could write it recalling all states with both spins. Then it comes with a factor of 2, which is a bit counterintuitive. And I've met physicists who've been successfully working in the field of superconductivity for more than 30 or 40 years, and when I showed them this formula, they automatically corrected the coefficient. So that factors of 2 coming from spin can be very confusing. But okay, let's forget about the spin. Let's just count at F levels without spin degeneracy as a function will be like this. Okay, so now we know ground state energy and its dependence on phase. We know the current in the ground state. That's the formula for current, which I've just obtained by differentiating energy. So current at low transmissions is low and almost sinusoidal. Current at high transmissions is the best realization of sawtooth in modern quantum physics. And in between we have curves going from sinusoidal dependence to this sawtooth. There is a jump in the current. If I will flash back these curves, you see that this is associated with a cut in the energy of Andreev state at ideal transmission. Fine. I guess it's about it. I want to say about Josephson tunnel junction. That's what I mentioned. Big-Baratov formula derived Josephson energy in terms of for Josephson junction, and they have been quite surprised that it does not depend on any other parameter than superconducting energy gap and normal resistance of the junction. So if you're experienced condensed matter physicists, they would find other parameters in the view, but they didn't. Right, then I guess it's time to switch to spin. I could think of making this lecture in 3 pieces rather than in 2. Or in simple words, who wants 15 minutes break right away? Let's vote. Okay, let's have 15 minutes break, then I go about speed, then we have another break, and I switch to force.